We have told you that if the leading coefficient of a quadratic function is positive, then the function has a minimum value and its curve has a minimum point. Whereas, if the leading coefficient is negative, the function has a maximum value and its curve has a maximum point. But for some reason, you prefer to think that if the leading coefficient is positive, the function should have a maximum value because there seems to be some correspondence there. But we do not decide results in science this way. So how is it that a positive leading coefficient indicates that the function has a minimum value rather than a maximum value, as one may think? Let's look at it. Let f of x, giving us ax squared plus bx plus c, be a quadratic function. Then, by the method of completing the square, we can express f of x as a multiplying the square of the expression x plus b on 2a, the result plus a fraction with numerator 4ac minus b squared and denominator 4a. We note to begin with that the term 4ac minus b squared all on 4a is a constant, and so it's not responsible for the growth or decline in the function. Now, if we want to study the growth or decline in the function, we have to examine the first term over here because it is the term which contains the variable. For a moment, let's denote the expression s plus b on 2a by a new variable t and denote the constant by s. Then we can write f of x as at squared plus s, noting in passing that by these definitions, t and s are real numbers. It's also important for us to note that the function t squared is a non-negative function. That is, there is no real number that we can square and get a negative result. The least we can get is 0. And so this function t squared has a minimum value of 0, which occurs where t equals 0. We get that by setting t squared to 0 and solving for t. Now, judging from the relationship between x and t, if x increases without bound, t will also increase without bound, and t squared will increase without bound. In symbols, we write, as t approaches positive infinity for increasing without bound. So as t approaches positive infinity, t squared approaches positive infinity. On the other hand, as x decreases without bound, t decreases without bound, but t squared increases without bound. Why is that? If you square a large negative number, you will get a large positive number. So in symbols, we have as t approaches negative infinity, t squared approaches positive infinity. And so, summarizing the two scenarios, we write, as t approaches plus or minus infinity, t squared approaches positive infinity. Now we have come to the junction. What happens if t is positive or negative? We look at them one after the other. We begin by letting a be positive. Now if a is positive, then as t approaches positive infinity, at squared will approach positive infinity because at squared is a positive multiple of t squared. And as at squared approaches positive infinity, at squared plus s approaches positive infinity. At squared plus s is the addition of a constant to at squared. Now at squared plus s is f of s, and so at squared plus s approaching positive infinity means the function is approaching positive infinity. That is, f of s increases and increases and increases and increases and increases without bound. A function which increases and increases and continue increasing obviously has no maximum value. Next, we show that the function has a minimum value in this case as follows. Because t squared has a minimum value and a is a positive constant, at squared also has a minimum value. And because at squared has a minimum value, at squared plus s also has a minimum value. Remember again, at squared plus s is the addition of a constant to at squared. So adding a constant to a function cannot change the direction. Thus, f of s has a minimum in this case. What is this minimum? Let's begin by finding where the minimum occurs. Now this minimum occurs where t squared is minimum. Why? Because t squared is what is driving the function. T squared contains the variable. We have noted already that t squared is minimum where t is 0. And where t is 0, x plus b on 2a is 0 because t is equal to x plus b on 2a. Now if x plus b on 2a is 0, x is negative b over 2a. So the minimum of the function occurs where x is negative b over 2a. We proceed to find the minimum value itself. So x equals minus b on 2a means f of s is a multiplying the square of the expression minus b on 2a plus b on 2a. The result plus the fraction with numerator 4ac minus b squared and denominator 4a. At this point we have 0. So we have a multiplying the square of 0 plus this constant. But the square of 0 is 0. So we have a times 0 giving us 0 plus this constant. So we are left with this constant 4ac minus b squared all on 4a being the minimum value of f of x in this case. So the pair minus b on 2a, 4ac minus b squared all on 4a is the minimum point of the curve of the function. A point in plane, remember, is an ordered pair of coordinates. And so it will be wrong to say that the minimum point is 4ac minus b squared all over 4a, comma, negative b over 2a. A point is an ordered pair, not just a pair. Now, on the other hand, if a is negative, then as t approaches positive infinity, at squared will approach negative infinity. Note that at squared in this case will be a negative multiple of t squared, and so we'll change the direction of t squared, or we'll change the direction when multiplied by t squared. And as at squared approaches negative infinity, at squared plus s will approach negative infinity. At squared plus s is the function. So what it means is that the function continues to decline forever. And so a function which continues to decrease without stopping cannot have a minimum value. The function in this case has a maximum value, and we explain that as follows. Remember, the function is at squared plus s, which is a constant. So at squared has a maximum value. That is why at squared plus s, which is f of s, has a maximum value. But why does at squared have a maximum value, you may ask? At squared has a maximum value because t squared has a minimum value and a is negative. We illustrate with an example. Now, let t squared be a member of this sequence, this increasing sequence, just for illustration. These are not the only values that t squared can take. Now, if we let a to be -2, representing some negative value, then our at squared will be a member of this sequence, 0, -2, -4, -6, and so on. That is, over here we have 0 times -2 giving us 0. Here we have 1 times -2 giving us -2. Here we have 2 times -2 giving us -4, and so forth. We see in this sequence that the values that come after their preceding values are smaller, and the maximum of them, which in this case is 0, occurs where t squared is minimum. So the maximum of -2t squared occurs where t squared is minimum. It happens to be 0 over here, but that's not the point. Assuming we started from 1 going, then this sequence would have also started from -2 going. And again, we would have found that the maximum will occur where this is minimum. So that's the explanation to at squared having a maximum, because a is a negative constant and t squared has a minimum. Now that we have shown how at squared has a maximum, it's easy to see that at squared plus a constant also has a maximum, occurring where t squared is minimum. We know already that t squared is minimum where x equals -b on 2a. And so if we want to find the maximum of f of x, we have to plug -b on 2a for x in the function. And that gives us this expression, leading us to 4ac minus b squared all on 4a as the maximum value. Thus, the pair -b on 2a, 4ac minus b squared all on 4a, is the maximum point of the curve of the function. So the formula for minimum or maximum point of a quadratic function is the same. The formula does not tell you that it is a minimum or maximum point. You have to decide that based upon the sign of the leading coefficient.